Welcome back to Math 130, Applied Algebra and Trigonometry. Today we're going to be talking about exponential functions, which means we should probably review the types of functions we've already talked about. We have already discussed linear functions, which can take the form ax plus by equals c, or y equals mx plus b, or f of x equals mx plus b. Those are all forms of linear functions. And I'm sorry, I have had to abandon the type tool. It keeps capitalizing letters that I don't want it to. Okay, we have also studied quadratic functions. Okay, and the quadratic functions have looked like this. Either y equals ax squared plus bx plus c, of course, where a does not equal 0, or it could look like the function of x equals ax squared plus bx plus c, where still a cannot equal 0 because then you don't have a quadratic function, you don't have any squared term. Well, today we're going to add to that a type of function called exponential functions. Just a comment about the other types of functions before I write out the exponential function. If you look at the linear functions, there is no power of the variable x higher than 1. For the quadratic functions, there is no power of the variable higher than 2. When we get down to an exponential function, it is written this way: y equals b to the x, or f of x equals b to the x. And as you can see, the variable x is the exponent. That's why it's called an exponential function. Now, we have to put some constraints on the base, which is why we're using a b for base. We have to put some constraints on that. This is only true where, or if, b is greater than 0 and b does not equal 1. Why in the world would we put those constraints on it? Let's move some things out of the way here. Okay, and let's think about that. Okay, if b is 1, we would have y equals 1 to the x. And 1 to the anything is 1 times 1 times 1 times. You're always going to get a 1. And if the base is 0, anything to the 0 to any power is going to be 0. Now I'm going to leave to you to put into your calculator this case and graph it on your calculator. And no, your calculator is not broken when you see the graph, but think about why it does that. All right, let's play Is It a Function? Okay, here are the contestants. Y equals f of x. Y equals -5, but not of x, but to the x power. Y equals -5 to the x. Y equals -5 to the x, and y equals -1 times 5 to the x. Pause the video and think of your answers. Here are mine. Yes, 5 to the x is a function. -5 to the x. No, it is not a function. It has a negative base. We cannot have that. Y equals -5 to the x. Yes, that is a function, because we are only raising the 5 to the x power. I didn't say anything about a sign outside of the base. The base itself cannot be negative. And finally, -1 times 5 to the x. Well, that's what this is. So yes, that is a function. Let's look at those functions more closely. y equals 3 to the x. And we're going to make a t-table. Okay, it is a function. I could use function notation here instead, but I'm going to use y equals 3x because that's what your calculator likes. And let's put in some values for x. Let's do -3, 0, 1, and 3 halves. And let's put 1,000. Okay, so notice what I did there. In a strange order, I did 0, 1, negative, extreme, and a fraction. That means I used all of the zone F numbers, or rather examples of zone F numbers. Okay, let's figure out what this is. If I put -3 in for the exponent, I'm going to get 3 over, or 3 to the -3, which is equal to 1 over 27. I'm going to get 3 to the 0th power, which is equal to 1. I'm going to get 3 to the 1st power, which is equal to 3. Then I'm going to get 3 to the 3 halves power. What in the world is that? Well, the denominator of 2 tells me I have a square root, and then I have 3 cubed, which is equal to the square root of 27, and which in turn can be simplified to square root of 9 times 3, or 3 square root of 3. So 3 square root of 3. And if I now do 3 to the 1,000th, I get 1.322 times 10 to the 477th. I am not going to graph that, but let's graph some of the others. All right, so -3 would give me a 1/27, so almost on the line, but not. At 0, x equals 0, I would be at 1. At x equals 1, I would be at 1, 2, 3. At x equals 3 halves, so that's at 1 1/2, I would be at 3 square root of 3. Okay, I do need a calculator approximation of this, and that is 5.196. So that's at 3 halves. So 3 halves is 1 1/2, and then I have to go up 5.9. So 1, 2, 3, 4, 5.19. So about there. And I can now connect these carefully for that classic exponential curve. Okay. All right, let's graph another one. Let's do this one in red. Let's do y equals 1/2 of x. Notice the difference between the two. Over here, in our original equation, we have an integer as the base, whereas in our new equation, we have a fraction. Oh, I have to put in the exponent to make it a base, and it is not just the 1/2, the 1 to the x, it is the 1/2 to the x. All right, so let's make a t-table for this one as well, x and y. And let's do -3, 0, 1, 3 halves, and 1,000. Although, once again, I may not graph that one. Okay, if we have, for the first -3 there, 1/2 raised to the -3. It's a negative exponent. So first I'm going to flip what's inside there, which is just like 2, that becomes positive. I got rid of that negative. So I have 2 cubed, which is 8. All right, so after that, let's do 1/2 to the 0th power. It is the whole thing raised to the 1/2, so it is equal to 1. All right, how about 1/2 to the first power? Anything raised to the first power is itself. So 1/2. And then we have this 1/2 raised to the 3/2. So that's like the square root, because that 2, of 1/2 cubed. So that's like the square root of 1 cubed is 1 over 2 cubed, 8. Okay, shh, don't spread this around, but I'm not going to rationalize this. I'm going to be graphing it, so I'm going to want a calculator approximation anyways. So 0.3536. I am not going to be able to graph it that fine, but there you have it. And finally, 1/2 to the 1,000th is going to give me, with the calculator approximation, boy, I'm going to have to go down here to write it, 9.33 times 10 to the negative 302nd. So I'm not going to graph that one either, but I am going to attempt to graph these other ones. So let me do it in red. I should have done that whole chart in red, I suppose, but it's easier to read in the other color, in white. Okay, so -3 and 1, 2, 3, 4, 5, 6, 7, 8. So somewhere around there. And 0, 1, and 1, 1/2, and 1.5 is at 0.4, and etc. So here we have continue on. Notice it never reaches 0, and both of these curves go through 0, 1. And in fact, in any case where you have just a base and an exponent equal to your y, your dependent variable, it will pass through that point 0, 1. Okay? And that is another reason why, if you put in 0 here, you have any base to the 0th power equals 1. There you go, on a graph. And just as a review, let's do the domain and the range of, well, both of these actually. The domain will be all real numbers. It goes infinitely to the left and infinitely to the right. That's our first equation doing that, and our second equation also goes infinitely to the left and the right, so it's all real numbers. Okay, the range. Notice neither of them will ever cross 0. Okay, they'll never even reach 0. So the range of both of these is all real numbers, y greater than 0. Let's make some room. And wow, time flies when you're having fun. That's all the time I have on this video. YouTube won't let me have enough time in one video to upload everything else I want to. So I will see you in part B.